No, Zara, how can you say 2? Second excited state. I'm not saying second state, second excited state. You've not studied, Zara. If you missed the class, you should have studied. At least should have gone through the notes and the video class. Only one class was there. Second excited state means n is equal to 3. So the
I
total,
was not able to study because we're currently shifting. So yeah, that's why I
you didn't
guess I missed that
study.
one. Yeah.
Okay, I heard that you've studied. So that's why I was thinking. Okay, Zara, then. Then see how much you are able to understand in today's atoms. From nuclei, you will be able to understand. But by the time, let us just
Yeah.
practice questions. And before the next class, Zara, like you have tomorrow's
Hmm.
off and all, so please study. Okay, take some time.
Yeah, I'm
Okay,
right now I was going through it. The first chapter, like that chapter I did, and then I was going through this
all right. So
notes.
total energy's formula is minus 13.6 by n square. So excited states are always one lesser. Means this is written lesser, but it is actually one higher state. You will see. Just take the video lecture also, Zara. I think it would be
Oh,
helpful for you. It's just 1.5 hour lecture, so that will help you. So here the total energy will be minus 13.6 divided by 3 square. That is minus 1.51 electron volt. Now, kinetic energy is always negative of total energy. So first part, kinetic energy will be minus of minus 1.5. That is plus 1.5 electron volt. Second part says potential energy of third excited state. Third excited state means n is equal to 4. So again, we'll calculate the total energy minus 13.6 by 4 square. So this will be minus 0.85 electron volt. So this is how you have to, one thing I told Memuna also in the last class, you will see if you see the video lecture also, that these values you should remember. E1, E2, E3, E4, E5, E6, at least till that part you should remember, because these become very confusing if it is not discussed. So this is minus 0.85 electron volt. So here we have to find out potential energy. Remember, total energy is always potential energy divided by 2. This is the formula, sort of formula only that you can remember. Total energy is basically potential energy divided by 2. So potential energy will be twice of total energy. It will be minus 2 into 0.85. Whatever is this will be the answer. Coming to the third part, if electron jumps to the ground state from this third excited state, from the jumps to the ground state means the final n is equal to 1. And initial n means the initial n is that it is jumping from third excited state. That is 4. So we have a formula 1 by lambda is equal to Rydberg's constant 1 by n final square 1 by minus 1 by n initial square. So 1 by wavelength is, this is 10 to the power 7. This is 1 by 1 minus 1 by 16. So when you'll solve this 1 by lambda will be 10 to the power 7. 16 minus 1, 15 by 16. So lambda will be 16 by 10 to the power 7 into 15. So whatever is it, that will be the answer. That will be the wavelength. So this is the first question. Have you copied the question, Zara?
I took a screenshot.
Of the question?
Yeah.
Okay, write down the solution then. Or you can take the screenshot of the solution also, because you will not be understanding right now much. So
Yeah.
after that, but please note it down in your sheet or wherever. Okay, take the screenshot
Okay, ma'am. Yes, I did.
and इसका भी ले लो.
Okay. Done.
Okay, Two more questions I have there, so that I'll tell you, but after revising, when you will study, you should be able to understand these. See, this says that this is the energy level of the hydrogen atom that is given. And it is saying find out the transition which results in the emission of a photon of wavelength 496 nanometer. Means wavelength is given as 496 nanometer. So what we are going to do, we are going to calculate the energy corresponding to it. If you have studied dual nature, in dual nature we have, yeah, you were there in dual nature, hc by lambda, remember?
Yeah.
So
Yes, ma'am.
using this, we'll calculate the energy first. So this will be 6.67 into 10 to the power minus 34. Speed of light will be 3 into 10 to the power 8 meter per second. Wavelength will be 496 into 10 to the power minus 9 meters. And I'll divide this by 1.6 into 10 to the power minus 19, so that I get the answer in electron. Whatever is this answer right now, I don't know. I have not calculated. But how to find out the transition? So see, n is equal to 1 is minus 13.6. N is equal to is minus 3.4. N is equal to 3 is minus 1.51 electron volt. These are all in electron volt. And this is fourth one, so minus 0.85 electron volt. Like this, we have the entire spectrum present. Now see, we will see the differences. This is 1, 2, 3, 4, 5, 6. We have to find out now which transition is corresponding for this wavelength. So we have calculated the energy. Let's say, for example, I am saying, just for example, I am saying that this energy is, let's say, 5 electron volt. Just for the example, this you have to calculate and check later. Now, I am seeing the first transition. First transition means from fourth to 3, means this one. So I'll take their difference. 2, 1 is from fourth to second. See, fourth to second. So I'll take the difference between 4 and second. I'll then calculate, likewise, I'll calculate all the differences. See, I have the energies and I'll calculate all the differences. Suppose this one comes out to be 5 electron volt. 4 to 3 means the answer will be 1. 1 will be the transition. Have you understood a method roughly?
Yeah.
Okay. And which transition corresponds to the emission of the maximum wavelength? See, for the second part, whichever energy is inversely proportional to the wavelength. Maximum wavelength, minimum energy. Out of all these, whichever will have the minimum energy differences, all these will have the minimum, which one will be the minimum will be the answer. Just take the SS of this also.
Done. Done. Done, ma'am.
Okay, one last question. So this is very easy and important question. Which level of double ionized lithium has the same energy as the ground state energy of hydrogen atom? Now, ground state of hydrogen, I'll see. Basically the formula of energy is minus 13.6 Z square by N square. This question is saying, Zara, that energy of the lithium is equal to energy of the hydrogen. Now, minus 13.6. Z for lithium. See, in your periodic table, hydrogen, helium,
Yeah.
lithium.
Third.
And this is 3. So, this will be 3 square, that is 9. By N square, we don't know what is N. Come to hydrogen. This is minus 13.6. This is 1 by N square. N is given as ground state of hydrogen. Ground state means N is equal to 1. So this gets cancelled. N square is equal to 9. N will be equal to 3. Means the third orbit of lithium will be equal to the first orbit of hydrogen. They'll be having the same energy. Okay, take the screenshot of this too.
Done.
Yeah, Zara, do you have these notes with you?
Yes, ma'am.
You have the notes, no? Okay. You've taken the printout?
Yes, ma'am.
Okay. So these numericals, no, try to adjust the numericals in the back of the sheet if it is there, because you'll have all the material together for this. All the materials
Mm.
for a particular chapter, it will be together. All right. So let us then start with nuclei only. Okay, yeah, Zara. So structure of the nucleus. So structure, see, we are studying atoms and nucleus, right?
Mm.
In the nucleus part, we have continuously studied about the atom, and in the Bohr's postulate, in the Rutherford's postulate, everything it was coming that this is basically the central core part is present, which is known as the nucleus, because of which the alpha particles were getting scattered and everything. So this will be clear when you are studying. When you study, then it will only be better. Now coming to the structure of a nucleus. So wait. Zara, just understand some portions from here. Whatever you want to add it in your notes, you can. Here, understanding from here will be better. Then you will be able to understand through the notes. Now, when we say nucleons, nucleons is a collective term for protons and neutrons. Because we are not talking about the atom now. The entire atom we have already discussed. Now, when we have the atom in the center, we have this nucleus. Now we are just talking about the nucleus. So this nucleus is made up of nucleons. Nucleons means the proton and the neutron. We are not talking about the electrons because electrons are beyond the nucleus. Atomic
Mm.
number is number of protons, that is represented as Z. Mass number is represented by A, which is the number of nucleons, that is number of protons plus the number of neutrons, that is what is A. So these things will come. Whichever point you wish to copy and anything, just let me know. I'll stop also so that you can add. Just let me know, Zara. Okay.
Mm.
Now, number of protons is Z, number of electrons is also Z, and number of nucleons, total, it's A. So if I say what is the number of neutrons then? So see, number of neutrons plus number of protons is equal to A. So number of
Mm.
neutrons will be A minus Z. So this is one part. Now coming to the notes part, before we go on to the isotope one, see here. Neutron is a neutral particle carrying no charge and having mass equal roughly to the mass of a proton. Chadwick discovered the neutron, and the rest of it, this point is important. A free neutron is unstable, and the mean life has just 1,000 seconds, is just 1,000 seconds. So mean life, average life, this you don't have to calculate. Many things are deleted in this. These are old
Okay.
notes when the syllabus wasn't changed. So nothing less is present, extra portions are present.
Mm.
So that I'll tell you. Like in
Okay.
atoms also, that's why I'm saying, see the video lectures also, many things are there extra. Don't do those things,
Okay.
waste your time. Yeah. So see, atomic mass unit is, in your chemistry, you must have heard that this is 1 by 12th the mass of a carbon atom. And you
Mm.
should just know that mass 1 AMU is a unit, which is 1.666 into 10 to the power minus 27 kg. Now, this part is not very much important. From here, it is important, this part. So whenever you start studying, start from atomic number and mass. Before that, it's
Hmm.
not very important. Yeah, one thing is there, this part, that the mass of the neutron, mass of the electron, and the mass of the proton. Sometimes in few questions, these have not been mentioned. So at least these three, try to remember these.
Okay, ma'am.
So start your preparation this chapter from this. So this I have discussed. Yeah, before isotopes and all, I'll explain you a bit here. Because you don't have to copy anything, everything is written. See, you have few structures whenever you write a chemical symbol. The topmost part is written like this. That is the number of nucleons, mass number. Number of
Yeah.
nucleons means the mass number. And the Z, that is the protonic number, is written in the downwards left hand side. So upper right corner is your mass number, lower left corner is your protonic number. That is Z, atomic number. So like this, if it is written, chlorine 35, 17. These 17 and atomic number, whenever you are calculating for the mass number, for the atomic number, it is always the list of the periodic table, the serial number of the periodic table. Hydrogen
Yeah.
1, lithium 2, lithium 3, like this. So chlorine comes at the 17th position. This is the mass of the chlorine. So this you must have used a lot in your chemistry for the mole concept. So I hope you are remembering all these. Now isotopes are what? When Z is same, means
Hmm.
the protonic number is same, but mass numbers are different. Like hydrogen has 3 isotopes, protium, deuterium, tritium, like this. What if same mass number is there, but different atomic number is there? Like chlorine and sulfur, both have the mass number as 37. That is the mass, 37 grams are there, but the atomic number is different. Sulfur comes before chlorine, or calcium and argon, both have the mass as 40, but 2018 argon comes first, then comes after that comes calcium. Isotones have the same number of neutrons, means you subtract it. See, chlorine and potassium, what is this? 37 minus 17, 39 minus 19. This is also 20. This is also 20. So such are isotones. And isomers are, they have Z also same, they have A also same, but they have the different energy states, means their compositions are different. Isomers, same thing, but energy states are different, means compositions are different. So these are some things. Now, coming,
I'll write down isomer part because it's not here.
yeah, right. Isotone is there,
Yeah.
right? Just add the line of isotone.
Done, ma'am.
Okay. Coming to the atomic masses. So this I was saying that for electron, proton, neutron, you should remember. Because in some questions, I have seen that it is not mentioned. Usually in the exams now, whichever question papers of pre-boards you people have sent, this was mentioned already. To
Hmm.
be on the safer side, you can just go through it and remember at least these three. Because this can be
Okay.
created. You can add it. Now coming to the nuclear size. Just understand this derivation. Small derivation is there. Yeah, I think it's just listen, then you can check the notes. Basically, whatever is the volume of the nucleus, whatever is the volume of the nucleus, it is directly proportional to the mass number. It is directly proportional to the mass number. So volume, let's say this is a nucleus, which is having the radius as r. So volume will be 4 by 3 pi r cube. It is directly proportional to A. 4 by 3 pi are already constant by themselves. So R cube is basically directly proportional to A. I can say R is directly proportional to A to the power 1 by 3. The cube sign will go on the opposite side. So R is directly proportional. So when we remove it, there's a constant that comes, which is R naught, A to the power 1 by 3. So it's a very easy formula and a very useful formula in your numericals. Directly the question will be given. See, what are all these things? What is R? R is the radius of the nucleus. See, this is what we chose. This is the radius of the nucleus. What is this R naught? This is 1.2 into 10 to the power minus 15 meters. So this is written as 1.2 Fermi meters. Usually you write the radius whenever the numericals are given. I'll show you the numericals also. That time we write this mostly as in Fermi meters only. But see, sometimes in few questions, the value of R naught is also mentioned. Then don't use 1.2 Fermi meters. Otherwise, usually the formula of R naught is taken as 1.2 Fermi meters only. 1 Fermi is equal to 10 to the power minus 15 meters. So this conversion you should just know. And what is A? A is the mass number. So you have to brush up with a little of your chemistry for atoms, nuclei. Like modern physics is used in your chemistry also. In 11th, you must have done all this. Okay, this is one thing. I'll give you time to write and everything. Just understand one more part. This is also very important and very easy part. Nuclear density. Density, we know the formula. Mass by volume. So mass of nucleus by volume of nucleus will give us the nuclear density. Now, what is the mass of the nucleus? Every proton will be contributing to the mass. Let's say this is mass into the mass number. This is how we do, no? Number multiplied to the quantity. So this is the number multiplied to the mass divided by. Volume of nucleus is simply 4 by 3 pi r cube. Now, R's value from here, R naught is equal to R naught A to the power 1 by 3. From here, you are going to write the value of R. Okay. This will be M into A 4 by 3 pi. Now, this will become R naught cube. A was already having the power 1 by root 1 by 3. So, this A will become A. 1 by 3 will be cancelled by 3. Basically, R is equal to R naught A to the power 1 by 3. If I am taking R cube, so it will be R naught whole cube A to the power 1 by 3 into 3. So 3 gets cancelled. You have just R naught cube by A. So A gets cancelled. Now look what are we left with. 3 M by 4 pi R naught cube. Now look, Zara here. 3 is a constant. Mass of a nucleon, the average mass of a nucleon, it's constant. 4 is a constant. Pi is a constant. R naught is also the constant. Remember this, R naught is also a constant. It means density is completely constant. So if I say the density of iron, if I say the density of cobalt, if I say the density of lithium, there isn't any factor that can change the answer, because there is no dependent quantity. If I put all the value, average mass of nucleon is done experimentally and calculated, that is 1.67 into 10 to the power minus 39. 3 you know, 4 you know, pi we already know it's 3.14. R naught is also 1.2 Fermi meters. When you put in all the values, you get a one fixed value only. So see, rho will be 3 point, what was it? 3 into 1.67 into 10 to the power minus 39 divided by 4. Now instead of pi, I'll write 3.14 Fermi meter. I'm going to write 1.2 into 10 to the power minus 15 whole cube. When you are going to solve this, this density will be 2.3 into 10 to the power 17 kg per meter cube. This is the density which is independent of anything. This is completely independent, this energy. It is just, this is universally constant. This is universally a constant. You take any metal, you take any element, you will be getting the density always as 2.3 into 10 to the power 17 kg per meter cube. Now,
Okay.
before let's go through the notes, then you can write down any point if there is lacking there. So isotopes we discussed, isotones, isobars, mass energy equivalence was already done. This will come ahead. R is equal to, yeah, this is written very less here in the notes, no? This you can add then here. Why have we
Okay.
written that part? Density is also not written properly. Whatever things are missing, that you can write. Before we go to the numericals, one thing, the forces between the nucleons. So this we'll be discussing first. I think you write down the portions from the density and from the nuclear cells.
Done. Done, ma'am.
Okay, Zara, first just listen to the questions, means just then you can copy it later. So it says that calculate radius of germanium given R. Now see, R naught's value is mentioned. So we will not take 1.2. We are going to take 1.1 since it is mentioned. Now R is equal to R naught A to the power 1 by 3. R will be R naught is given as 1.1 Fermi meters. A, see, mass number is mentioned here, 70. The top one is the mass number. So cube root of 70. That is 4.12. So 1.1 into 4.12. This will be 4.53. But since we have not converted any unit, the unit here will be in Fermi meters. If you want, you can put and write this as 4.53 into 10 to the power minus 15 meters also, depending upon your question. Write this question first.
Okay, ma'am. Ma'am, how did we calculate 70 raised to 1 by 3?
Cube root of 70, long division method.
Hmm. Is there no like easy way?
No, see, how I did was like 70 is there. So 4 into 4 into 4 is around 64. So this gives an
Yeah.
idea that, yeah, in the long division method, in your 8th class, I think you must have done square roots and cube roots. There was a chapter. So this gave an idea. Yeah, 4 can be related to 70. So 4.1, then like this, through the long division method. That's how only that can be done. Okay. So just brush up your cube roots and square roots.
Yeah, we get those questions, but
Because in the radius part, cube will come.
yeah, usually the numbers are like you can get them into cube roots and then you can
Sometimes, yeah.
just cut them up.
See, these are rarely given actually, Zara. 27 is given like this. 6
Yeah, that,
is given usually. But yeah, this is a question from your textbook only. So if such questions are there, so practice them and it's not difficult. Even if you're writing it, see 4.12 and 4, they are very close. So use some hit and trial method also. If long division is seeming a little difficult, hit and trial से एक बार देख लो तो इतना अंदाजा तो लग गया ना कि 4 ही होगा कोई भी नंबर है मान लो
I got that.
yeah, you will get an idea. So around it,
Hmm.
27 की जगह मान लो 29 है. So you know it will be 3
Hmm.
something only. So
Hmm.
usually the numbers are there in the form of in the product of threes only. That is like 27, 64 and all. Cube roots ही रहते हैं usually. Cubes. Done, Zara?
Ji, ma'am. Done.
So express 16 milligrams into equivalent energy. So that was the formula which we have done in dual nature also. In atoms also this came. And now in nuclei also, we just read it. That is E is equal to mc square. So that's a very basic formula, Zara. E is equal to mc square. Mass देखा और energy पूछी गई है. Don't think of anything else. Even if an additional portion is mentioned, just straight away focus on E is equal to mc square. Einstein की equation है. Mass क्या given है यहाँ पे? 16 milligrams. So you have to convert it 10 to the power minus 3. Speed of light, Zara?
3 into 10 raised to 8 meter
Yeah,
per second.
3 into 10 to the power 8 meter per second. Correct. So whenever you have questions based on this, so mass is 16 into 10 to the power minus 3. Speed is 3 into 10 to the power 8 whole square. So this, when you will calculate, this will be 9 into 16. So 144. 16 minus 3. So 13 into 10 to the power 13 joules. This will be the energy. Write this also.
Okay. Done, ma'am.
Okay, coming to the next question. Assuming proton and neutrons have equal masses, calculate how many times nuclear matter is denser than water. Basically, it is saying density of nucleus to pata hai, density of water bhi pata hai. Now compare them. How many times nuclear matter means nucleus only. So density of nucleus is just a 2.3 into 10 to the power 17 kg per meter cube. Now, density of water is also very clear that this is 1000 kg per meter cube. So, density of nucleus by density of water when we'll take, so 2.3 into 10 to the power 17 by 10 to the power 3. So 14. 2.3 into 10 to the power 14. So you will say the nuclear matter is this much time denser than the density of water or denser than water. Clear? One more thing before you note this question. Tell me the answer of this question. Just read the question and tell me. What should be the answer of this? Nuclear mass of iron is given this 55.85 AMU. What should be the nuclear density?
The same 2.3.
Yes.
It's
So
for
it
all the.
also there because it is independent of the mass. Nuclear density will always be 2.3 into 10 to the power 17 kg per meter cube. So even however the question is confusing, don't get confused. Write this only for the nuclear density. Just pay attention which density has it mentioned. Density of atom or density of nucleus. Okay.
Okay, ma'am.
Write down these two questions as well.
Mom, can you scroll down? Done now.
Okay, Zara, coming to these points. So the force between the nucleons. So this is, let's make an estimate of the magnitude. Basically, the gravitational force which you have studied in your class 11th. So if you remember, the formula was G m1 m2 by r square. That is the universal gravitational constant. Masses, here we are taking two protons. So the masses of protons are taken by r square. So when you put the values, you get this. Similarly, the Coulombic force, you have calculated this here only. So when you put this, you get the ratio as the electric force is 10 to the power 36 times stronger than the gravitational force. So this is written just because Coulomb's law is there in your syllabus. So if it relates, this can come. So this is the ratio. 10, okay, 10 to the power 38 it is. Okay. Now, properties of the nuclear forces. They are 10 to the power 8 10 to the power 38 times as strong as gravitational forces, means strongest forces in nature. Short range forces, because it is calculated in Fermi meters, they are strong attractive forces. The nuclear forces are strong attractive forces, and repulsive forces, like attractive for the protons, repulsive for the, sorry, attractive for the electrons, repulsive for the proton. They are saturated forces, means experience only due to its nearest neighboring nuclear, means they are range forces. The range is short. If anything is there apart from their vicinity, they are not able to experience it. So nuclear forces are charge independent. They do not depend upon the charge. Nuclear forces are spin dependent. Spin means the electronic spin, plus half, minus half of the electronic spin that is there. And they are non-central forces, like Coulomb's law. Coulomb's law always acts in the line joining the two charges at the center of the, means on that line that joins the two centers of the charges. This is independent force. It has a range that has to be covered. So potential energy of pair of nuclear as a function of distance. So see, this is the potential energy. This is just a graph. Basically, this graph shows that, see, potential energy is there. Then as the distance is increasing, potential energy decreases. It becomes zero. And then there is repulsive forces. There are repulsive, distance is increasing from the nucleus. Okay. Then see, this distance is there. This distance is 0.8 Fermi-meters. This distance, when the this is the minimum distance for which the potential energy is the negative, means maximum negative. See, for potential energy, जितना नेगेटिव होगा उतना अच्छा है, बिकॉज पोटेंशियल एनर्जी फोर्स का फंक्शन है. सो जितना नेगेटिव का मतलब होता है कि जितना स्ट्रांगली अट्रैक्शन ऑफ फोर्सेस होंगी उतना ज्यादा पोटेंशियल एनर्जी इफेक्टिव होगा. सो हमारे इस ग्राफ में दिस इज द बेस्ट पॉइंट. So this distance is 0.8 fermimeter, and then it decreases. This is the graph which you have to remember. So it's a minimum at this distance. It's attractive for larger distances. Okay. Coming to this whole concept of, I'll explain you this there on my OneNote. I'll explain you. It will be better for you to understand it. See, the concept of mass, everything is written here, there only. See, total mass of protons. See, mass of a single proton is mp. So if there are 2 protons, 2 mp, 3 protons, 3 mp. Z is the number of protons. So Z mp is the total mass of protons. What is the total mass of neutrons then? Number of neutrons into mass of a single neutron. Mass of a single neutron is m small n. A minus Z is number of neutrons. So A minus Z into Mn is the total mass of neutrons. So you have total mass of protons, Zmp, total mass of neutrons, A minus Zmn, and total mass of the whole nucleus, not the atom, but the nucleus, total mass of the entire nucleus. That is, I have written it with M, capital N. Now, this mass defect is just basically, you're just assembling all these. Okay. Whenever, see, mass defects are there in your system, mass defect means whatever is the change in actual mass is there because of energy loss or some sort of losses, the mass can change slight, very slight. So how do we write? Total minus whatever is it. Suppose right now, this much of mass is there. Earlier, this much was there. So how much has increased? This part. How do you calculate? Total minus what is it now? So Zmp means the total mass of protons plus the total mass of neutrons minus the total mass of the nucleus, whatever is it. This is how we write this. That's it. This looks very big, but when you'll calculate, only the problem is that the point things are there. And when you multiply the change in mass with the speed of light square, see, this is like your formula E is equal to mc square. So mass is the mass defect, E is the binding energy. Now, what is this binding energy about? See, when the nucleus is formed, okay, whenever the nucleus is formed, there is energy freely available. Why? There, when the nucleus is there, suppose this is getting broken into 2 smaller parts. So whatever was the energy that bound it, okay, that was binding it initially, now is getting released. So that's the binding energy. Okay. So this is what is there. So the formula is calculate the mass defect multiplied by the square of speed of light. So how can I write it completely? Zmp plus A minus Zmn minus Mn into C square. And for one single nucleon, if you have to write, so that will be binding energy per nucleon. You divided by the mass number for every nucleon, divided by the mass of every nucleon, you will get this formula. Now, binding energy is also written instead of sometimes writing this entire speed of light and calculating. See, you will write 9 into 10 to the power 16 meter per second, and then because 3 into 10 to the power 8 whole square, and then converting your answer into electron volt and something. This is often used in the calculation. See, this is your mass defect. This is 931 mega electron volt. Straight away write your answer in this. Most of the questions are solved by this formula. And if you have to calculate binding energy per nucleon, calculate binding energy using this formula only. Okay. So now I'll show you the notes which you were writing. Then we'll come to this question. Wait. Okay, Zarasi. A mass defect is the difference between the sum of the masses of the nucleons constituting a nucleus and the rest mass nucleus. This is called the mass defect, denoted by delta M. So how do you calculate? ZMP plus A minus ZMN minus MN. MN means the mass of the nucleus. Now, what is this binding energy? When nucleus is formed from the free nucleons, the decrease in mass of the nucleons is released, whatever I told you. See, the earlier this energy was holding the nucleus. Now the nucleus has broken. So whatever was the energy will come out, and that is your binding energy. So energy equivalent to mass defect is used in binding the nuclear, and it's called the binding energy of nucleus. In order to break the nucleus or to completely separate the nucleons, it has to be greater, obviously. Binding energy is making your nucleus bound, intact. So you need a greater energy to release it. So formula is mc square, you multiply, and moreover use this formula. Delta M into 931.5 is usually not written. 931 mega electron volt is written. And binding energy per nucleon, you have this formula, you divide it by the mass number. Packing fraction is not there in your physics. This will be there in your chemistry. Okay, this last graph is left. So let me discuss the graph. Then one numerical is left from that binding energy that will complete. So remember, Zara, till page number, what is this? 6 only revise and study. Don't learn anything from page 7 onwards. This is not there in your syllabus. Okay?
Okay.
Entire alpha, beta, conservation of energy, nuclear level, nothing. Radioactivity, कुछ भी नहीं है इसमें से. कोविड के बाद से सब डिलीट हो गया, पहले इंक्लूडेड था. Till this only study. Now let me discuss what is this binding energy curve. Then we can practice that one numerical which is left. Basically, इस curve में ना ये shape important है ज़रा. This shape can come. And this basically is plotted and was done experimentally. Binding energy per nucleon, like in this method, whatever we have studied, for every element it was taken. So there were certain variations observed. See, this graph is not smooth. This is not a graph which is like this. This isn't like this. You can see hydrogen, helium tak to theek hai. Lithium ke liye it drops down. Then there's another kink like this. And ultimately after 56, that is iron is achieved. Then the graph becomes a little stagnant and it decreases. So this is a shape. This is the shape of the graph. This is there in your syllabus. It is important. It can come. So whenever it comes, draw this and write these points. That's all what you have to do. Nothing else is going to come from this graph. No numericals, nothing. So see, let me read the main features of the plot. So you understand binding energy versus mass number is given, right? So
Yes.
see, it is practically constant, that is independent of atomic number for nuclei of middle mass. Means जिन जिन का mass number 30 और 170 के बीच में lie करता है, उसके लिए usually it is independent. See, independent. But the curve has maximum, ये peakest point, अगर peak point जो आएगा ना graph का, that is 56 iron. Remember this. This is asked. The peak point of this graph is the iron, 56. Now, binding energy is lower for both light electrons. A is 30 or the mass number is more than 170, it decreases, it starts decreasing. Till here it is more, till this point. Now, what can you conclude from the two observations? This is your important observation from the graph. What did you see here? See, 30 till here, this is 30 and this is your more than 170. See, this is your till 30 part and this is your more than 70 part. So this is relatively constant. If you see, this is not obviously a straight line, but almost it is straight, near to straight. So this is what is written. Middle mass number के लिए independent हो जाता है, इसलिए constant हो जाता है, practically constant. Iron पे peak observed है, ये एक important point है याद रखने का. Maximum value iron पे, जिसका mass 56. This you have to remember. And one thing is there, this is lower for this also, and it is lower for this also. Means these are the heavy nuclei and these are the light nuclei. Tell me, Zara, first, you've understood these 2 points?
Yes.
Okay. Now, what all conclusions we can say? Force is attractive and sufficiently strong to produce binding energy for few mega electron volts. This is short ranged, as we have discussed earlier. This basically tells us about the nature of the nuclear forces. Nothing very much related to these individual atoms. It just gives a brief view about the nuclear forces. So it's short ranged. The property that a given nucleon influence, only nucleon close to it is also referred to as saturation property of nuclear force. Heavy nucleus like A is equal to 240 or something for uranium, it has a lower binding energy compared to that of 120. See, 121 here, and this is lower. So this is a variation. What does this imply? This implies energy would be released in the process. It has very important implication of energy production through fission. Now, if A is very much less than 10, like these one, hydrogen, helium, the isotopes of hydrogen are mentioned. See, H2, H3, then helium is mentioned, then lithium. So this says that two light nuclei joining to form a heavier nucleus. Binding energy per nucleon of the fused heavy nuclei is more than the binding energy per nucleon of the lighter one. Okay. This means that final system is more lightly bound than the initial system. Means energy must have been released somewhere. That's why the final energy is more lightly bound, okay, than the initial system that was present. So these things you have to remember for this graph, but remember these from alpha decay you don't have to do. So moreover than these conclusions, these 2 points, main features of the plots are important, which you can elaborate. And here you have to write down the properties of nuclear force. Now, Zara, write down this question.
Okay.
Zara, are your vacations going on?
Yes, ma'am.
Just to complete the C, this completes with the nuclei also. So we are just left with the semiconductors. So for semiconductors also, I'll provide you notes and the practicing of the questions we'll do. So that also requires one class. So if Saturday morning we can have the class, like your syllabus will be then completed by Saturday, because on next Tuesday I'll not be able to take your class. Then it will,
Yeah.
yes, fine. Just tell me a time
Yes,
on
ma'am.
Saturday, any time.
Anytime I'm free.
Okay, okay, then I'll just confirm with the team, then I'll tell you, okay?
Yeah, because we have like the second pre-board later, like not from next week, but after that.
Yeah, that's why I wanted
Just
to
to
complete the
finish.
syllabus before, because your other chapters are also left and all. So until we complete this, so then classes will be, I'll take your class on Tuesday morning also instead, because in the evening I'm not available. But at least mornings we can have the class for the time being.
Yeah, yeah, morning is better for me.
Yeah, okay then. But just tell me a minimum time that when do you get up usually? Because it's winter and your vacations.
I wake up in the morning, like at 8 or 7 a.m.
Okay, okay, okay. Okay, sir. Written?
Yes, ma'am.
Okay, see. Now we have to find out binding energy per nucleon of
Mhm.
this atom. That is calcium, mass number, atomic number we have. Now mass of neutron, proton and the nucleus. All the things have been mentioned in the question. Firstly, remember we calculate ZMP. Always calculate them separately, Zara. If you just put it everything in the formula, no, you will be applying your board mass and everything, and you'll not get the answer because these are very lengthy. And one thing remember, Zara, never round it off. You'll get your answer as
Okay.
1, 1, 0, 1, 0, 1, 0, because these are so less values. Never round it here in nucleus. Now,
Okay.
Z is given as 20. So 20 into 1.008665. So I have all the values calculated. So I'll tell you, this is mass of neutron I have written. Mass of proton is 7825. ZMP. MP is 1007825. So this is 20.1565 around this. Now, what about the mass of neutron? So A minus Z into the mass of neutron. A minus Z, 40 minus 20. This is also 20. So 20 into what's the mass of the neutron? 1.08665. This is around 20.1733. Then we have the mass of that. But before that, see, let's add these two. So this will be 89213.04. So this is what? This is ZMP plus A minus Z into Mn. What do? We subtract this with the mass of the atom, right? The mass of calcium is given as 39 point, what was it? 96. 962589. 962589. Okay, so when you will subtract these two, you're going to see, you are going to subtract these two. So it will be, the change in mass will be 0.367. Now understand what I have actually done it here. This is 0.367. The formula of change in mass is ZMP plus A minus Z Mn minus the mass of the nucleus. Look, Zara, I have added these two and then I have subtracted these two. Clear how delta M has been calculated?
Yes, ma'am.
Sure, you've understood?
Yes, ma'am.
Okay. Now, this was saying binding energy per nucleon. So, binding energy per nucleon, I have told you, take the mass defect, multiply it with 931. So, you'll get your answer in mega electron volt. Okay, this is mega electron volt. Divided by the mass number, that is 40. So, I think the answer will be around 8.541925. This is the answer. This is the binding energy per nucleon. So this is not very tough, Zara. It's actually simple. So do always calculate this separately, add these two first, and then subtract. If you put everything in this formula, you will think what kind of tough maths you are doing. Okay,
Yeah.
write down the solution.
Okay, ma'am. Ma'am, can you please scroll?